morning. I think you've heard the announcements before. Well, maybe not all of them. Our volleyball team, today's the 25th, just 3 shopping months left till Christmas, okay. But they're playing Gadsden State this evening. Unfortunately, it's in Gadsden. So if you happen to be driving through Gadsden about 6 o'clock, stop in and cheer them on. Then on the 30th, which I can't figure out what day that is yet. Is that Monday? No, Tuesday. It's Saturday, 29th, Sunday. Monday. Right. On Monday, they'll be playing both Coastal Alabama and South and Wallace State Selma. Coastal Alabama South will be at 4 o'clock, and Wallace State Selma will be at 7 in the evening. Both home matches. Huh?
Where is Coastal? That's where the Superintendent of Education money, right?
Coastal?
Coastal, where is it located?
Well, that's the thing.
Mobile or someplace.
Yeah. See, there were several small community colleges down in southern Alabama, and they decided to merge different ones together and then merge again. So they called the new one Coastal. I think the one at Faulkner State, I think, was one of them. If there wasn't one Mobile that may be in it, I don't know. Is Bishop down there? I don't recall. There were several down there. Maybe one of was Lurleen Wallace somewhere down there? I don't know. There were just several that they combined together. They either had 1 or 2 mergers, and the latest one, they've named the college Coastal. Was this yours? Coastal Alabama Community College, and because some of the ones that they merged already had volleyball programs in them, they named one Coastal East and the other Coastal South. So. So it's a group of bunch of them. There is a little bit of speculation, I don't know how serious, that at some point we're going to be merged with somebody. I just don't know if that's going to happen or not. We used to be, this campus was Western State Technical College. We were merged with Lawson, but we're still one of the smaller schools. Jeff State is pretty big. Certainly, Bevel State is really big. It's a merger of several ones. Huh?
I said, but it's closer.
Yeah. And so there's a bunch. Shelton is pretty good size. So I don't know. I don't know if we're going to be merged or not. But what they've been doing to other schools, I wouldn't be at all surprised. Now, it may not be while I'm still around. That'll be fine with me, because that means we go through another sax visit. But if I can avoid that, that'll be fine. But yeah, it's several of the colleges that were down in the coastal area. I'm guessing there was one in Fairhope or somewhere there. Was that Faulkner? I don't remember. And anyway, there's several down there, and several of them were merged together. I don't know where Chattahoochee Valley is. That may have been one of them. I haven't been to enough of the meetings lately to keep up with anything, so I don't know. All right. That was the first of the announcements. The others, I think you've heard, College Scholars Bowl, still recruiting people, and the NASA Community College Aerospace Scholars Program deadline is October 16th. Okay, let's get going from the current slide. And I'm pretty sure that example 7 is not on the slide set, so we're using this one. And example 7, I think, may be the last example in 12.4. All right, here we have, we started this last time, didn't we? But it just looked like it was going to get a bit too much to do in the short time we had left. So let's see if we can knock it out now. The position vector for a projectile shown in figure 1227. So I guess I need to show that projectile for it to make sense. Each of these is 25. Okay. And each of these will be 25. Okay. So the position vector for the projectile shown in this figure is R of t is equal to 50 root 2 I really don't like writing it this way, but that's okay, 50 root 2 t I plus 50 root 2 minus 32 t I'm sorry, there's a t there. I knew there had to be. Minus 30, no, minus 16. My eyes went to the wrong line. Okay, minus 16 t squared. J. Okay, I think I wrote it right this time. Position vector for the projectile shown in the figure. I haven't shown it yet, but let's see if I can do it. This may not be exact, but it's going to be close. Somewhere about there. Okay. And it continues on from there. Says find the tangential components of the acceleration when t is equal to 0, which is right here, t is equal to 1, which is there, and t is equal to 25 root 2 over 16. Okay. All right. Find the tangential components of the acceleration when t is equal to each of these three values. Okay. Now, just as this is probably not fair, but I'm going to do it anyway. This is a projectile. Because you see this component and that component are the same, that means the initial velocity was at 45 degrees, right? And it must have been 50, okay? Okay, 50 feet per second squared, yeah. 50 feet per second, because the acceleration is 32 feet per second squared. So really we know more about this problem than probably we should, but it's not necessary to know, but that's just what it is. All right. It says find the tangential component of the acceleration. Well, in order to do that, if you remember back, I'm sorry, a sub t, the tangential component of your acceleration has, I'm sorry. Okay. Hopefully that'll be a little better. The simplest calculational form is this one, V dot A over magnitude of V. Velocity dotted with the acceleration divided by the magnitude of the velocity. Okay? So in order to get that, we need to find the V, which is r prime, and that would be 50 root 2 I plus 50 root 2
T.
no.
T is out.
Yeah.
So then you got minus 32 there.
Minus 32t j. Okay. So let's go, sorry, and do the acceleration vector while we're here. And what would that be?
First part is just going to drop out, so you just get minus 32. Yes, minus 32J.
Yeah, perfect. Okay. And while we're here, let's go on and do the magnitude of the velocity vector. In other words, the speed. All right. Say again?
Big numbers.
Yeah, it is. That's the 2,500 times 2 would be 5,000 minus, plus, always plus. You've got to square that one. And you get another 5,000. And then you got minus 100 root 2 times 32. So let's make it 3,200 root 2 t. I hope that's right. Oh, he showed up. I mean, no, he's here. Okay, good. All right. Here's Josh. Just missing Corey. By the way, the other person whose name I've been calling, as far as I can tell, never paid because they removed her from the roll. So we just have those three. Okay. We're doing example 7, bottom of page 851. This is chapter 12, factor value function, 12.4, tangent vectors and normal vectors. And what we have is a projectile fired from the origin here. It goes up somewhere there. We don't know exactly where T1. Here's T is equal to 25 root 2 over 16. Okay? One of my favorite numbers of all time. Okay? Now, they gave us the displacement vector for that, r of t, and we took the first derivative to get the v of t and the second derivative to get the a of t. So we've done that. Right now we're in the process of finding the magnitude of v of t, which you can call the speed, and that would be the square root of this thing squared. Well, 50 squared is 2,500. And root 2 squared is 2, so that'd be 5,000. So that's where that one came from. Then when you square this, you got to square the first, twice the product of the 2. Well, 2 times 50 is 100, times 32 is 3,200, times root 2, and then all we've got to add is our t here. Whoops. Gotta get my pen back. T here. And then you square the last term. 32 squared. Let's just leave it as 32 squared for now. 32 squared t squared. Okay. We might need to square it later, but I'm going to see. Okay. So that is that squared. Well, 5,000 plus 5,000. Let's go on and make that 10,000. As Bill said, some pretty big numbers here. Okay. 10,000, and we'll make that a minus. Okay. 3,200 root 2 t plus 32 squared t squared, just because I don't want to deal with that yet. All right. Now, surely there's some things we can take out of that. Okay? One, for instance, is I know 4 will go into this, and 4 will go into that. 2, 5, 0, 0. Right? 4 will go into that again. 6, 25. Is that right? Okay. Now, I don't think that anything else will. So we could get 16 out of all of it. So check me on that and see what. Square root of 16 is 4. Wait. Yeah. So now check me on that and see if 16 into 10,000 is 625. It is. Okay. 625 minus, and 16 will go into that, 200 root 2t, and 16 into that. Now this is going to take, it's 64, I think. Because 16 would go into one of the 32s twice. That leaves the other 32 times 2 would be 64 t squared. Now, I think that's all we can easily get out of there. Now, they did something different from us, from what I did, by leaving that a 50 squared. And I'm not exactly sure why they did that. I bet there is a reason. But anyway, let's see what happens. Now, I've already written up here what your A of t is. It's v dot a. So let's do the dot product here. Well, this times 0 is 0. Okay. And this times that would be minus 32 times 50. Is that minus 1600? 32 times 50. I believe that's right. (1600) root 2 minus 32 squared, or plus 32 squared. Okay, first, that one's a minus, this is a plus. T. Okay, so there's the dot product, I believe. Divide that by 4 times the square root of 625 minus 200 root 2 t plus 64 t squared. All right. I know 4 will go into this minus 400 times. Okay, and 4 will go into that. 8 times 32 8 times 32. Second? 256. That's what I was thinking. Yeah, 256. Okay. All right. All right. So let's see what we've got left. Minus 400 root 2 plus 256 t. Yuck. This pen is so slow that I can't see where it's writing, and I write over it. Okay, that's the numerator. Denominator is the square root of that thing, which is 625 minus 200 root 2 t plus 64 t squared. Now, that's your a of t as a function of t. A sub t as a function of time. So, when we put in t equals 0, which I thought I had written somewhere, but either didn't, I guess I just said it. Oh, I said it here. T equals 0, 1, and that. So when t is equal to 0, so a, the tangential component of the acceleration when t is equal to 0 is minus 400 root 2 over the square root of 625. Now, someone check and see if 625 is a perfect square. That's not 125 times 125. That's way too big. 25 times 25, is that right? Yeah. Okay. So that would be 25. So it would be minus 400 root 2 over 25. I think I know what the answer is. It better be. And 25 will go into this minus 16 times. Now, I'm having a problem here. Oh, no, it's okay. So this will be minus 16 root 2. Goodness gracious. Okay. Let's see if that's what we got. Yes, minus 16 root 2, which is about negative 22.6. Okay. Now, why is that the case? Well, your tangential component of the acceleration is, the only acceleration is downward, okay? Well, you have, and this is your velocity, and your velocity is decreasing over time, so your acceleration is going to wind up being negative. And so at least for a little bit, that makes sense, okay? The value, maybe not, but, well, hard to say, but the fact that it's negative, that does make sense. Now let's do when t is equal to 1. Okay. So a of 1, a sub t of 1, that is minus 400 root 2 plus 256 divided by the square root of 625 minus 200 root 2 plus 64. Okay. Now, that's a lot messier looking number than what we had. See, I think ours is a lot better. You could have written that 625 as 25 squared and whatever, but I don't think any of that helps any. You just have to plug in the numbers and see what you get. Now they factor out, which is a perfectly legitimate thing to do, factor out a 32 in numerator and denominator. We didn't, but you could. And that'll make your numerator look a little simpler. But that gives you the tangential component of your acceleration. They claim, I'll trust them on it, is minus 15.4. And they don't give units, but whatever the units would be, feet per second squared, probably. And this one down here is approximately negative 22.6. Okay, probably feet per second squared too. All right. Now the tangential component of the acceleration when you plug in t is equal to 25 root 2 over 16. I sure don't have room for that anymore, so let's see if I can make some space somewhere. What is the least useful thing here? Probably this over here. I think we've already beat this to death, so I hope I don't need it anymore. I can't get my erasing mechanism to work very fast. There. I think that does it. All right. So A sub t at 25 root 2 over 16 that's equal to minus 400 root 2 plus okay, 16 will go into 256 6 times, I think, won't it? No. Huh?
16.
Second?
16 and 256?
Right. 16 times? Yeah, okay. That's what I was thinking. So that's going to be, where is it? Okay, there it is. So it'll be 16 times 25 root 2. Okay, over whatever your denominator is. I'm not going to mess with it. Why? Because 16 times 25 is 400. So this is a plus 400 root 2 minus 400 root 2. It doesn't matter what the denominator is, that's going to be 0. Okay. And that's all you needed to do. Okay. And they showed that as well. Okay. So from the picture there, if you didn't trust my picture, which I would not suggest you do, yeah, that is where it reaches its maximum. Okay. So it reaches the maximum height when t is equal to 25 root 2 over 16. There, the tangential component of the acceleration is 0. After that point, the acceleration will start speeding up, going down. See, tangential component of this, everything I do here is going to be a velocity, but if you picture it, the velocity is slowing down, so the acceleration is also negative. Tangential component is negative. The speed is decreasing as it goes up, and that's what that depends on. And when you get here, that tangential component is 0. Coming down, now the speed is going to be picking up again, so that tangential component of the acceleration is going to be positive from then on. The normal component, which is always perpendicular to that, is basically, I think will probably be negative just about throughout. I can't see how it would be otherwise, but they didn't ask that, so let's not muddy the waters. That does finish 12.4. Any questions on that? I know that was pretty messy, but it's all doable. Homework exercises here would include any of the odds 3 through 7. They're all at Calc Chat. 5's at Calc View. 9 through 13, all at Calc Chat. 9's at Calc View. 15 to 19, all at Calc Chat. 15's at Calc View. 21 and or 23, both at Calc Chat. 25 through 29, all at Calc Chat. 27's at Calc View. 31 or 33, both at Calc Chat. Any of the odds 35 to 39, all at Calc Chat. 35's at Calc View. You can look into or explore doing 41. That should be at Calc Chat as well. I would say either 43 or 45, both at Calc Chat. Any of the odds 47 to 51, all at Calc Chat. 53 and or 55, both should be at Calc Chat. 57 certainly 57, 59, either of those two should be at Calc Chat. 61 is a little different kind of problem, so you might want to take that one on. It's up to you. That should be at Calc Chat. 63 should be at Calc Chat. So you can just do one of those four if you wanted to. Orbital speed, 65 or 67 should be at Calc Chat. True false, 69 should be at Calc Chat. 71 is a motion problem, but that's, using hyperbolics, so you don't have to do that if you don't want to. The 73 and 75 are both proofs. If you're really into those, you can certainly look into that. And then the final application of, I guess you'd say application of vector value function is that of calculating arc length and curvature. That's the next section. Any questions before we leave 12.4? All right, let's see if I can get out of this. Wow. Yeah, here we go. .5 arc length and curvature. It'll come up one of these hours. Here we go. Okay. Still in Chapter 12, vector value functions. And 12.5, arc length and curvature. So here's our objectives. If you had to sort of guess the first one, we'll find the arc length of the space curve, three-dimensional. We'll use the arc length parameter, which we haven't defined yet, but will, to describe a plane curve or a space curve. We'll find the curvature of a curve at a point on the curve. Enough curves in that sentence. And we'll use vector value functions to find frictional force, which doesn't quite seem like it fits the others, but it is a pretty good example. So let's start with arc length. So the formula for arc length in a plane curve, now we're in 2 dimension now, plane curve, has a natural extension to a smooth curve in space. Now we're in 3 dimensions, stated in the next theorem. If you remember what it was in 2 dimensions, here's how it extends to 3 dimensions. C is a smooth curve. Now remember what smooth means. No corners, no cusp, no breaks, smooth curve, meaning everything's differential. Okay? If C is a smooth curve given by R of t is equal to x of ti plus y of tj plus d of tk, pretty generic form, on some interval a to b. Okay? So it only has to be smooth on that interval. Then the arc length of that curve on that interval is little s, and it's the interval from a to b of square root of x prime squared plus y prime squared plus z prime squared dt, which is basically your integral from a to b of your velocity, the magnitude of the velocity vector, in other words, the speed vector. So the arc length is the integral of the speed. Strange way to say it, and it probably is a very good thing to say that way, but that basically is what it turns out to be. Okay? As a function of time, of course. Okay. Now, example 1 shows find the arc length of the curve given by R of t is equal to ti plus 4/3 t to the 3/2 j plus 1/2 t squared k. And we'll do that from t equal 0 to 2 as shown in this figure. Okay? Thank you for drawing it. I sure didn't want to. Okay? And as t increases from 0 to 2, the vector R of t traces out the curve. Here is that curve. It starts bending this way and it's bending back that way. Thank you for drawing. Okay. So what are we going to need to know before we can calculate that arc length? Say again? Of what? R of t, that's perfectly fine, and you can do it that way. That would be the shorthand, so let's do it. R prime of t is equal to I plus two t to the 1/2 j plus tk. Is that what you said? Perfect. Okay. Now what do we do with that? Take the square root of it, or the magnitude of it. So the magnitude of this R prime of t is equal to the square root of 1 plus 4t, right? So when you square t to the 1/2, you get t.
Oh, yeah, sorry.
Right?
Yeah.
Okay. Plus t squared. Now, that came close to being a perfect square, but it's not, is it? If there had been a 4 on the first or a 4 on the last, that would have been okay, but it's not. So anyway, there's your R prime of t. Okay, what do you do with that now?
Find out what, plug in T,
What's that?
plug in the T's.
Plug in what?
Plug in 2 and then subtract.
Okay, well, what we got to do, if you think back, is it's the integral of that, right?
Find the integral substitution somewhere.
Yeah. We do the integral from 0 to 2 of this thing. Square root of 1 plus 4t plus t squared dt. Now, not a, perhaps the best integral you've ever seen, most inviting. There's something you need to do with that to make it a little.
I'll take the square root sign off and put a
1 to the 1/2. Okay, that's okay. I like that idea too. I'm not sure it's going to get us anywhere, but I like the idea.
Just makes it easier for me.
I see you have to do a substitution of some kind to get that thing fit something.
Right. And a regular, what do they call it? U substitution. You don't have any du out here that you can simplify anything with, so that's going to be a problem. So it almost has to be a trig substitution, but it isn't in your standard form for that. So basically, and my one inclination is to write it in ascending order of powers. I think of those a little bit better. So let's do that. Let's write this as t squared plus 4t plus 1. Okay. Now, mostly because I glanced at the book to see what their approach was, they're going to complete a square. Okay? And this is where you would be heading if you're doing a trig substitution. You'd have to go that route. So basically what I'm going to do with that then is say a t squared plus 4t blank plus 1. Okay? Now, what I put in the blank here is what it would be necessary to do to have complete the square, to have a perfect square trinomial. And what would that be? I sort of said it earlier. Yeah, just divide 4 by 2, that would be 2t, square that, or 2, square that, and you get 4. So plus 4. But I just changed the problem. So I better do a minus 4 out here, right? Okay. Now, this gives us t plus 2 squared minus 3. So that's now what's under the radical. Okay? So let's see if that gets any better. Integral from 0 to 2 of t plus 2 squared minus 3 dt. Oh, wait. That's to the 1/2. Wait, no. I put the 1/2 in the wrong place. That squared, this is to the 1/2. Okay. Now, is that any better? One could argue maybe no. I'm beginning to regret turning think it would matter. That's kind of, in a small way, beginning to look like a secant. Is it? Yeah. Yeah. A secant substitution, I believe. Because those usually are of the form, and you can either go to the, I can't remember if it's front of your book or back of the book.
So that's one of these lookups, huh?
What's that?
That's one of these lookups, huh?
Lookups, is that what you said?
Yeah.
That's what I typically do to keep from spinning wheels too long. I don't see what I'm looking for there at the front. I saw something close. Let's go to the back. There's a table back there. Well, maybe I have this marked. No, I don't. Maybe I have it marked there. Yes. Okay. At least closer to it. Okay. This is a form of the square root of something squared minus something. And let's see what we've got. If you had a u in front, that would be helpful. We don't. All right. Is 26 probably about as close as we're going to get? If you're in the back of the book, I don't know if you are back there, it's on page A4, which is not very useful, but it's somewhere in the back before your index, before your answers to odd number problems. You're in that ballpark there, and here's what it is. Number 26 says the integral of the square root of u squared, I'm going to use the minus because that's what we got, minus a squared, okay, du. Now we got a little bit of messing to do, but I don't know what just happened there. There we go. Okay. That will be 1/2 open parentheses u times the square root of u squared, and we're going to do minus a squared, the square root of u squared minus a squared, and then we're going to use the minus a squared minus, wait a minute, no, a squared times the log of the absolute value of u plus square root of u squared minus a squared. Goodness gracious, this is such a pain in the neck. Is a plus. The square root of u squared minus a squared. Okay. Plus c. We don't need the plus c. Forget that. Okay. We got definite integral. All right. Now let's identify what's what. Our u is t plus 2. Okay. Our a is the square root of 3. Okay. And I think that's it. And everywhere you see a square root of u squared minus a squared, and you see them in 3 different places there, that's just this integral right here. So what we're going to have is 1/2, or goodness gracious, u, which is t plus 2, okay, times this thing right here, the square root of t plus 2 squared minus 3, okay, minus a squared, which of course would be 3, times the log, I'm going to write this down below, natural log of, well, I could probably get it, no, natural log of t plus 2 plus the square root of t plus 2 squared minus 3. Okay? Right. And we're going to evaluate that from 0 to 2. All right. Whew. So we say. Oh, no. No, I think that's fine. Because we haven't done any substitution, we just looked it up. All right. So let's see what we got. 1/2 of 4. I got that part okay. Times the square root of 16 minus 3 right, minus 3 times the natural log of 4 plus the same thing, the square root of 13. Okay? Now, that 1/2 is times this whole thing here. Okay? Minus, when you plug in the 0 there, you'd have, I've lost it now, there it is. Okay, there we go. 2. Well, I have the 1/2 in front of it. Well, that's right, you're right. Let me take off this bracket here. Yeah. Don't put that bracket in yet. Okay.
It's easier to multiply all at once.
What's that?
It's easier to multiply all at once at the end.
Yeah.
Maybe.
So what we have then is, goodness, it's finding it on the page. Okay. Wait, okay. Let me put this bracket in too. Okay. That would be helpful. Okay. 2 times the square root of 4 minus 3. I can do that one. Minus 3 times the log. Oh, okay. Yeah, there's minuses of minuses.
It just has to multiply.
Okay. No, we're going to wait and do the 1/2 at the very end, I think. Okay. Whew. Log of, that's going to be a 2 there, and the square root of 1. That's just going to be a 2. Okay. All right. So let's see what we got. 1/2 of 4 root 13 minus 3 log, and we don't need absolute value, 4 plus root 13 minus 2 plus 3 log 2. I think. Okay, so the 1/2 will wipe out a 2 here and wipe out that there. So I think what we got is 2 root 13 minus 3 times the log of 4 plus root 13 minus, did I do something really stupid there? I think I need a 3/2 here. I think I wiped, I divided 2 into those two, but that would be a 3/2 here and a 3/2 here, I think. Okay. Minus 1 plus 3/2 log 2. Okay, I'm not sure I'm right here, but let's see what we got. We could leave it like that, or we could sort of group terms together and say 2 root 13 minus 1 minus 3/2 the log of 2 over 4 plus root 13. I don't know if they go that far or not. Let's wait. I think it's a plus there. A plus there. I don't know. Let's see. Where are we? Okay, 2 root 13. Got that. Minus 3/2 log of 4 plus root 13. Got that. Minus 1 plus, I should have left it just like that. Down at the bottom. This is how they left it. They didn't try to group or simplify anything else. This right here. Whoops. Too much. No, that's right. Okay. Nope. All except the very last.
What was this file?
It's log 3, not log 2. I don't know how I wound up with a log 2 there. I messed that up somehow. When I plugged a 0 for t b.
We just didn't add the square root, which was 1.
What's that again?
Like in the corner there by the 6, the ln is going to be 2 plus the square root of 1.
Ah, that's it.
I've been trying to figure that out for like 10 minutes.
2, oh, this is a plus here is what you're saying. Right, okay. Yeah, I left off my plus sign. Okay. And square root of 1 is 1, so that would be a 3. Okay. We saying came so close. All right. And that's what they got. Amazing, but true. Okay. That was a plus 1 there. I completely lost focus on everything towards the end there. Okay.
Could you explain something then?
Okay.
Why would he pick the example where you got to look up an integral or something, and then you got to go back and then now while you look up trying to find the integral, you forgot what the whole
Problem was about, right? Yeah. I don't know, especially for the first example in the section, you know, which is supposed to sort of start out a little easy, and then you can work up to harder ones. But starting out this way is. But now here's the other thing.
Don't get much harder, right?
Yeah. Well, here's the thing. If you remember back when we did arc length in 2 dimensions, you know, I remember saying, hey, these are almost crazy problems because you have to come up with some function that when you take a derivative of it, square it, add 1 to it, take a square root of that, you get something you can integrate. Same problem here, only in 3 dimensions. So it's not going to be pretty. If you found something that did work really nicely, that would look really awful up there, you know, because something that meets all those criteria is just nuts. Because think about it. What did we do? We took derivative of this, then we squared those components, and then we took the square root of that. Now, the one thing we didn't do was add 1 to it. I hope we weren't supposed to, but probably did. But anyway, yeah, it turned out something pretty horrendous. But coming up with an equation that wouldn't, that might be harder to do than doing what we just did. But yeah, we wanted him to come up with the hard part and let us do the easy part. But yeah, these, anytime you deal with arc length, it's going to get messy because you're taking functions, squaring them, adding them together, taking a square root, and then trying to integrate that. And that's not a pretty picture. Never is. And it's going to be a really hard thing to find. What makes it even worse is, oh yeah, that's right. Okay, I was going to say they didn't even tell us how to do it, but he did say Appendix B, Formula 26, which I didn't look at, but that's where we wound up anyway. All right, messy. Let's see if they did anything that make it a little bit better. Okay. Using x of t is equal to t, y of t is equal to 4/3 t cubed to the 3/2 power, and z of t is equal to 1/2 t squared, you obtain x prime of t is 1, so y prime is 2 t to the 1/2, and z prime was t. We did all that. Okay. So the arc length is then given by the square root of each of those squared, which, the way we did it, we just did the square root of the speed, which is the same thing, okay? And when you put all those down, you get the same thing we did. Integral from 0 to 2 of square root of 1 plus 4t plus t squared. Now, without telling us why they went to this thing. The only reason to go to this form is to try to get something either you can substitute or you can find in a table. Because I don't think you'll ever find that in a table, okay? Not specifically with those numbers. So try to get it into a form that might be in the table. And this form is in the table where this is your u and this is the square root of a squared, which that is your a. So you need an a squared there. And that's where you, on this, they don't even tell you to go look in the table. They just do it.
So that's my cool thing. It's what he got down here where he did the substitution, saying, okay, remember that we're going to have to complete the square here.
Yeah.
And, give us something.
Yeah,
so
give us something.
All this time and forget about what we were supposed to do.
Yeah, exactly. We lose the forest for the trees, yeah. And, yeah, that's exactly it. And I agree with you. An extra word or two in just a couple of places here would have made that a lot cleaner, and easier to follow. And then to jump from this step to that step as if you knew that right off the top. I mean, if I look at that and say, now wait a minute, how did he do that integration? He doesn't even say here, go to a table in the back and see this. Because I look at that and say, is that supposed to be intuitively obvious? No, it's not. It's taken straight out of the table. And anyway, I agree with you. It's a mess. Then you plug in the numbers and you get that. All right. Now, they're skipping example 2, so let's us go back and see if we can do anything with example 2. Hopefully we can. Find the length of one turn of the helix given by r of t is equal to, oh good, we don't even have numbers, b cosine ti plus b sine t j plus the square root of 1 minus b squared k. No, tk. I looked at the wrong line again. Square root of 1 minus b squared tk. Now, they show you the picture in the text, and I sure can't improve on that, and anything I'm going to do is going to make it look pretty rotten, but I'm going to try not to make it as rotten as possible. Stop somewhere about here. Okay. That's not very good. And it's going to be even worse when I erase. Okay. So let me try that one more time. Starting here, going up here, and then when you get right back around here somewhere, you've done one turn. Now that's ugly, I admit. Okay. All right. Now, one turn here means the t is going from 0 to 2 pi. It gives you one turn, right? So this would be, when they say one turn, that translates to 0 less than or equal to t less than or equal to 2 pi. I think anyway. Okay? Yeah. Okay. Okay? Now, what would you do next? R prime of t is equal to cosine t I j plus. Now, this one, if you don't mind, I'm going to write it as 1 minus b squared. Well, no, that's just a constant. Okay, who cares? It's just the square root of 1 minus b squared k, right? B is just a number, so that's just a number. All right. And then what? The square root of, yeah, you take the magnitude of that. Okay, and what would that give us? B squared sine squared t plus b squared cosine squared t plus b squared, right? Okay, good deal. Now, the first part here, these first two, let's group those together. Factor out a b squared, and you have the square root of b squared times 1, so it's b squared plus 1 minus b squared. Hey, that's going to be pretty easy, isn't it?
I think so. That's 1.
Okay, that's going to be 1. All right.
I can do this one.
Finally, okay. So that's going to be your, what your integrand is, okay? So basically you're going to have, what is it we're looking for anyway? The length, okay? S is equal to the integral from 0 to 2 pi of dt, right? And what is that? Okay. I probably should have done, I just went straight to the chase. Sorry about that. Okay. That would be t evaluated 0 to 2 pi. And that's 2 pi. Okay. They did find one that's easy. Okay. But that probably would have been a little too easy for us at the very beginning. We'd have thought they all were going to be like that. I don't know.
Well, tell me,
Yeah.
when you saw that sine squared plus why don't we just jump up, just throw a 1 in there automatically?
Do what now?
Well, you saw the circle, this part, where you see the circle, you know this part's going to be 1.
Yeah. That part, yeah.
Okay.
But you got to
Why
factor
don't
out.
you just say is that what you did when you say b squared? You say b,
Yeah.
b squared
I
times
factored out
1.
the b squared here, and the rest of that's going to be a 1
Yeah.
plus 1 minus b squared, which is what's left there. Yeah, that's what I did. I skipped too many steps.
No, you
I
didn't
was
skip
better.
anything. And said, I'll be looking at that, and I said, okay. Yeah, you can still got the factor. I just say, this is going to be 1.
Yeah,
That's
okay.
what I'm going to do.
Yeah.
Okay. That's all right.
All right. Yeah. I could take a few more like this and a few fewer like the previous one. Right.
Oh, yeah.
But the previous one probably a little closer to the reality. This one, look, you had to have a really weird z component. The square root of 1 minus b squared t.
Wouldn't thought it would have ended up like that.
Yeah.
Yeah, but what would happen if, I'm trying to see if we had a different configuration for the z component.
Right.
This wouldn't come out as nice as that.
Oh, definitely not. Yeah.
Yeah, okay.
In fact, you probably go.
One turn.
Yeah.
So we can kind of guess at that anyway.
Right.
If we didn't know anything else, say one turn is going to be 2 pi, no matter what we do.
Yeah. Well, the thing is, if you had figured out by, I don't know, the radius is b of this part right here, what that would be is a circle of radius b. Okay, and what they did is that's the radius part, and by doing this as the how far it goes up, it basically would almost be like you see if this is right. I'm just guessing at this. Take a spring with just one loop to it, radius b. I'll take that and move it up, and that just that height, and that's what you got, and that would be the arc length, and that would be the height you would do to keep it at that radius or something like that. That's what you've done. You've taken that and gone up that far. Strange, but true. I guess, okay. I didn't quite say that the way I wanted it to be. But anyway, let's move on to, let's see, yeah. Arc length parameter. Now this is something that comes out so neat formula-wise, but it's just about impossible to get to. But they love it, okay? Definition of the arc length function, and later we're going to call it the arc length parameter, okay? Let C be a smooth curve, just like before, okay? RT, by RT defined on a closed interval, A to B, where A is less than B is less than B. And the arc length function then would be S as a function of T. What you do, the very thing we had before, when we just had S here, that was the integral from A to B of R prime of T dt, right? Magnitude, that, go back right here, and S is equal to the integral from a to b of the magnitude of r prime of t dt. So what we're going to do now is, like Fundamental Theorem of Calculus Part 2, I believe it is, we're going to make this a function of t, which means we can't use this t there anymore, so we change that to any other dummy variable. They're using u, and then put the t up here, a to t. So now this is arc length as a function of t, and these will be your u's here. That's exactly what they've got here. So this, okay. S of t, now it's a function of t. You put your t up here in the b spot, and then it's r prime, magnitude of r prime of u du. This is just a dummy variable. T is now your variable of interest. But then this definition is same as before, the square root of x prime squared plus y prime squared plus z prime squared, all times du. The arc length S is called, this thing here, I would have said arc length S of t, is called the arc length parameter. Is that S of t. Now, so they write it here just like they did there. It says absolutely nothing for me here except here's where t is equal to a, and then it curves around, does whatever it's doing here, and winds up at t is equal to b. And the arc length parameter for that curve here is that S of t. Okay. Now, so what in the sense are we doing? Well, anyway, that's what the arc length parameter is at any time t along that curve from A to B. Anytime t along that curve, this is going to be your arc length parameter. Okay. Using the definition of the arc length function we just showed there, and the second fundamental theorem of calculus, which I've been referring to, we conclude that ds dt is equal to r prime of t. Okay? Go back for a moment here, because if you do ds dt, you do a ds dt here, and basically you wind up with this thing. The derivative undoes the integral, and you wind up with that, and that's ds dt. So that makes for a really interesting little situation here. When you're talking about r prime, you're taking the derivative of your r function, which has vector components, and you have all that mess that you're dealing with. But see, S is a scalar. That's just the arc length of all that mess, okay? And if you do the derivative of your arc length, you just got your speed along that curve. How much the arc length changes over time, that's the magnitude of speed. That's not the same as r prime, that's a vector. But your speed is a scalar quantity. So it's the ds dt is just simply your speed. If you think in terms of displacements, okay? Derivative of the arc length function. If you're not dealing with displacements, it's still the, it's now just called the arc length parameter. You don't talk about it in terms of speed. In differential form, then you can write this as ds is equal to magnitude of r prime dt. Thinking in terms of motion, this would be your change of your arc length is your speed times your time interval. So that's almost distance equal to rate times time. I mean, it's almost that simple. Speed times time. Okay. Let's do example 3. Find the arc length function S of t for the line segment. The line segment given by R of t is equal to 3 minus 3ti plus 4tj. T is going from 0 to 1. And then write R as a function of the parameter S. That's going to be a bit different then, but okay. All right, so what have we got to do? Okay, let's take a derivative. R prime of t, okay, we got to hurry, is equal to what?
Minus 3, 5, plus 4, j.
J, got it. And then what are we going to do? Second?
Square each component.
Okay, take the magnitude of it. Okay, and that would be the square root of? Yeah, 25, which is 5. Okay. That's your R prime of t. And then what do you do with that? Yeah, integrate it. Okay. All right. Your S of t is equal to the integral from a to t of 5, I'm going to put 5 on the outside, du. Think that was legal, right? Okay. So this will be S of t is equal to 5. Oh, and our a is 0. Okay. 5t. Okay. That's it, right? So S of t is 5t. Now, that's the first part. Find the arc length function S of t for the line segment given by that. Okay? Now, what they say that next is write R as a function of that parameter S. Okay? Well, here your x of t is equal to 3 minus t minus 3t, right? So this tells us that t is equal to s of t over 5, right? In other words, s over 5. Got that? Well,
So you just
Okay.
divide the 5?
yeah.
I mean, I get that. And then
Yeah.
you put that into the x of t.
Exactly. Okay. So this would be 3 minus 3s over 5, right? Which would be, if you, I don't know if you wanted to do this, but that could be, I don't know, you could write it as 15 minus 3s. I don't know. I think it'd be easier. Well, that's perfectly fine like this. Or you could have done 3 times 1 minus s over 5, if you want to do that. Okay. But anyway, there is x as a function of s now. And do the same thing here. Your y of t is equal to 4 times s over 5. So that would be 4/5 s. Okay? So now writing r of t would be, I don't know which form's better. Which one do they use in the book? No, they leave it in the first form. This one here, I think. Well, almost that one. 3 minus 3/5 S I plus 4/5 S J. Okay. That's how they do it. Okay. And you think, is this supposed to be anything better? I like the other one better. Okay. This is just messier, but there it is. Oh, it's not R of T. This is R of S now, not R of T, because now it's a function of S, not of T. Okay. Now I think, oh no, we got a few more minutes. Okay. All right. Now, one thing we didn't do, we didn't put our limit on S. But here we see when t is equal to 0, S is equal to 0. And when t is equal to 1, S is equal to 5. So this will be 0 less than or equal to S less than or equal to 5. So really, to get the arc length parameter that's equivalent, you need to put the limits on it. And those would be equivalent. Again, that form's look a lot neater than this one. Okay. Now, one of the advantages, let's see, maybe, let's see how they did it, okay? Because R prime of t is minus 3i plus 4j. R prime of t, the absolute value of that would be 5. And S of t would then be the integral from 0 to t of absolute value R prime of t du, which would just be 5 du, that would be 5t. Done, just like you said. S is equal to 5t. So, turn that around and make t equal S over 5. So then you can rewrite R in the arc length parameter form, and you do this with your X, do it with the Y of t, and now get a new value X of S and Y of S, and that's what you got. R as a function of S is 3 minus 3/5 S I plus 4/5 S J.
Why are we using U? I don't even see the point.
What's that?
Why are we using the variable U at all?
You could make up any variable you wanted to there.
It doesn't.
It doesn't. It's a dummy variable.
Okay.
It's just something to fill the place. You just don't want to use t.
Because you'd be using.
You're using t up above. Yeah, that's the only thing. And they always did that with fundamental theorem of calculus part 2. Whatever your variable was originally, move that up here and put a different variable down there. You could use stickman for a variable. You could use, C or, row or anything you wanted to, because it's not going to show up anymore anywhere else. Once you evaluate it between those two things, it's gone. So it's just a dummy. Just don't use t. Anything. All right. Now, so anyway, we've done this. We've written it that way. Oh, they leave out the next part. I wish I was looking for the next part. So let's us put it in. One of the advantages, in fact, in my mind is about the only advantage of writing a vector value function in terms of the arc length parameter is that your magnitude, so let's go back, let's take it one more step here. All right, there we have it. There's your R of S. Let's see what your R prime of S is. What would that be? I'll do is magnitude. Okay, 3/5 squared would be 9/25, 16 25ths, and that's equal to 25/25ths, which is 1. The derivative of your arc length perimeter is always 1. Okay? That's the only advantage I can see. Well, later we'll see some others, but basically it normalizes your speed, basically. You're saying this is, I don't want to quite use the term unit vector. Well, it makes your R of t a unit vector. No, it makes R prime of t a unit vector. Okay? Which is your velocity in terms of your arc length. It makes that speed a unit vector. Okay. So, I think that's what they're going to get at in the next. We're almost out of time. Theorem 12.7, arc length parameter. If C is a smooth curve given by R of S is equal to X. Okay, now we're in the arc length parameter. X of Si plus Y of Sj. R of S is, or in the space curve, R of X of Si plus Y of Sj plus Z of Sk, where S is the arc length parameter, then the magnitude of that arc length parameter squared, the R prime of S, the magnitude of that is always 1. Moreover, if T is any parameter for the vector value function R such that R prime of T is equal to 1, then T must be the arc length parameter. Okay. And you might be thinking, as I was thinking,
what is T?
If T is any parameter that makes this true, this is true for a parameter T, then T has to be S, the arc length parameter. Most of the time that's not going to be true. The magnitude of any old function R prime of T is not going to be 1. If it does turn out to be 1, they say, hey, that's the arc length parameter. It's just going by a different name. All right. And we'll start next time at curvature. But let's see. Yes, we did example 3. So, homework exercises here. Woo. Woo. All right, would include any of the odds 3 through 7. They're all at calcchat.com. Do number 9 is at calcchat.com. Do any of the odds 11 through 15. They're all at calcchat. 13's at calcview. 17's at calcchat. And stop there. We'll pick up curvature next time. Now, I think I had said, because this is the last section here, I didn't get them run off. If you want me to go run off that test, I'll give you an extra weekend to work on it. Let me see if I can find it. My memory is I had to kludge together a couple tests to make it work. But let me see if... Okay. I don't know if y'all are familiar with the term kludge. I just sort of made it up. All right, yeah. My memory is not great, but it's there. Okay, there's 3 of you left in the class. that's not it. Don't tell me I've lost my. There it is. Is that it? That's it. Goodness, how did it get way over there? Okay. So, this is going to look a lot longer than it is. What it is, because we did the
11.6.
yeah 12.6, it's on what I at one time called test 1, and then what we did in chapter 12 is on test 2, and I didn't get these reconfigured, so I'm going to give it to you this way. And let me just go make the copies quickly. Let me end this because I'm recording all that.